So we're approaching the end of our unit of study, and we're going to begin to discuss what happens when you continuously apply a force to an oscillating system as opposed to just giving it one impulse to set it into motion. So here's what I'm talking about. In our study of force vibrations, let's just start with a reminder of the type of vibrations we've studied so far. If you have a mass on a spring, and we're not going to ignore any more air resistance, we'll assume there can be a force equal to negative BV, and there's also a force from the spring equal to negative KX. Well, when we pull this back one time and then just let it go, then it's set into motion, and the result is a exponentially decaying vibration. Okay. What about, here's a form of a pendulum you've experimented with before. Take some metal chain, put a little rubber strap, another metal chain, put a child on it. You know where I'm going with this. And then you give them a push. Now, you want to set them into a form of a human pendulum. You just want to push a child on a swing. Well, I don't think many people come up to this child and just give one hard push and then walk away and set it in motion. No, you push once a little bit and they swing a tiny bit, and when they come back you push again and they swing a little higher on the next swing, and after enough repeated pushing, then they reach the maximum amplitude they're going to get to. And so this is an example of a forced vibration. You're applying a continuous force to set the object into motion as opposed to just letting it go once and leaving it to its own. So this is what we're talking about when we say forced vibrations or driven oscillators. If you drive the system at a steady frequency, push, wait, push, wait, push, wait, and that push matches the swing, there, back, push, back, push, there, back, push, right? So the frequency at which you drive the system we'll call omega D, the driving frequency. And then I want to define something called omega naught. Now let's keep our study limited to the case of the mass on a spring. So for the simplest mass on a spring, it has what we call a natural frequency. And that natural frequency, you probably know, is just equal to the square root of K over M. Okay. So now we have three forces to consider. There's the force from the spring, negative Kx. There's the force of air resistance, negative BV. And then we're going to apply a driving force, F subscript D. And that's just equal to some value F max times cosine omega dt, our driving frequency. And so if you factor all these together, the end result, without going through the full derivation, the resulting amplitude of motion is equal, not surprisingly, to the maximum force applied in the numerator divided by, well, a lot of other terms that you'll have to take at face value. I'll spare you the derivation. But it's not a surprise the quantities that show up. The stiffness of the spring is a factor, and the stiffer the spring, the smaller the amplitude given a certain force. So we see K in the denominator of this equation, minus M times the driving frequency squared, and then this whole expression is squared, plus B squared times the driving frequency squared. That's it. So, I want you to consider the case where the driving frequency happens to be equal to the natural frequency. What if we did that? What if we drive a system at the frequency it most likes to vibrate at? Then we can make a substitution into this equation, and we can replace omega d with the square root of K over M. So we would get A equals F max divided by the square root of K minus M Okay, so if driving frequency is equal to natural frequency, but then we have to square the driving frequency in this term. So omega squared would be equal to k over m. So m times k over m, the m cancels out, and now we're just left with k minus k, which is 0. And so it doesn't really matter that we're squaring this term. This all becomes 0. And the denominator becomes b squared times k over m. So we get a is equal to f max divided by b times the square root of k over m. So that's the greatest amplitude you're ever going to get, right? Given an equation like this, since everything here is squared, it's all going to be positive, and there's a plus sign. And so to make the whole denominator the smallest possible value, we need to make this term here go to 0. And the only way this term goes to 0 is if the driving frequency is equal to the natural frequency. So, for example, if the driving frequency is greater than the natural frequency, in other words, if the driving frequency is greater than the ratio square root of k over m, then this term in the denominator, represented by k minus m omega d squared, all quantity squared, plus b squared omega d squared, right? For the case where our driving frequency is greater than the natural frequency, then this term is non-zero, and because it's all squared, then we're just basically saying the whole value in the denominator increases, and so the amplitude is less than it would be in this critical case where the driving frequency matches the natural frequency. Maybe it's best to try to state this point I'm making with a graph. So I just want to present you a graph of the amplitude of vibration compared to the driving frequency. So if your driving frequency is too low, let's put a value on here that represents natural frequency, which in turn is equal to the square root of k over m. So if my driving frequency is anything less than that, then you have very small amplitude. But as you get closer and closer, as the driving frequency approaches the natural frequency, the amplitude of motion reaches a peak value. And now for values of driving frequency that are greater than the natural frequency, then the graph falls off again. So you get the greatest response when the system is driven at its natural frequency. That's a concept known as resonance. So resonance is the idea that, how should we say this? The vibration of a system is dramatically affected by the driving frequency, and when the driving frequency matches the natural frequency, you get a very rapid increase or very large growth in the amplitude of vibration of the system. That's the best way to say it. Resonance is a condition when driving frequency matches the system's natural frequency there's a large increase in the amplitude of the vibrations. That still might be hard to relate to without some examples. So let me give you an example of a resonant condition I remember from my childhood. The house I grew up in had windows of all different shapes. So one bedroom window was relatively small, maybe another bedroom window was bigger, and okay, that's good enough. So if you go up and you tap on a window, if you just flick it with your finger, bang on it, bang, the window likes to vibrate a little bit. It has a natural frequency, and small things vibrate rapidly, and large things with more inertia vibrate more slowly. Well, I lived in the flight path of the helicopters back when the Marine base was still operating El Toro, which is now the Great Park of Irvine. That used to be a large marine base, and the helicopters flew in a line right over my house, right over the elementary school I attended, and the sound of these helicopters was a very common sound from my childhood. And the helicopter's blades made the sound poop, 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 poop. There was a steady frequency to them, and it actually was very nearly matched the frequency that this window liked to vibrate at. And so it happened to, even though the helicopters were way off in the distance, with their helicopter blades making this noise, poop, 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 when they were miles and miles away, you couldn't even see them yet. If you were outside and looking, you wouldn't know that the helicopter was approaching. Yet if you were inside the house, there was sort of an early detection system because the window would start to vibrate rapidly. There was a large increase in the amplitude just due to the fact that there was a driving force produced by the motion of the helicopter blades that matched the natural frequency of the window. The most famous example of resonance is a bridge near Seattle, Washington in the 1930s. It's called the Tacoma Narrows Bridge, or the Tacoma Narrows Bridge collapse. Gosh, if you were to Google that, you'll find all sorts of results. I'm going to post a video for you, and fortunately, way back then, nobody had cell phones with cameras built in, but somebody showed up with a camera, and there is footage of this bridge collapsing. Essentially what happened, the bridge spanned a river gorge, and it was a suspension bridge, and it was, it was a technological marvel, really. There's these big spans here. Now, wherever the supports meet the bridge, that represents a place where you can't have any vibration. But the bridge actually acted kind of like a giant guitar string. When the wind blew, it had to get around the bridge, so the wind either has to go over the top of the bridge or the wind has to go underneath. And when it does that, if you ever notice when water does this in a stream, it doesn't just create a steady flow, but there's a little bit of turbulence, and you get these things, eddy currents in the wake of the wind, and that creates a region of low pressure right here. And that low pressure on this side of the bridge compared to this side creates a driving force, and that driving force under normal conditions caused the bridge to vibrate up and down. And so the whole bridge would vibrate up a little bit, I'm exaggerating, and back down. And cars drove across it. Now the bridge, I don't even think it lasted for a year before it collapsed, but cars would drive over it under these moderate wind conditions, and I think they nicknamed it Galloping Gertie. So that was the thing to do, is sort of like a thrill ride to drive your car across this bridge. And it's perfectly safe. You might remember about Young's modulus and bulk modulus. Concrete and steel can withstand the compressive forces and the forces of tension involved with the bowing and flexing of the bridge. But at a higher wind speed, something peculiar happened. The bridge was set into a different mode of vibration. And so instead of just having these things called nodes right here, nodes are points where you can't have a vibration. Obviously, you can't have a vibration where the bridge meets the support. So the supports represent nodes, and under normal circumstances when the whole bridge was flexing up and down, then this whole region that's flexing is called an antinode, and that's the region of greatest vibration. Well, at a higher wind speed, there was a forced node in the midsection, and so it caused two antinodes. This region of the bridge was one antinode, and this region of the bridge was another, and it caused the bridge to twist about this point. And you'll see it in the other video that I'll have linked. And concrete and steel doesn't have a very large elastic limit when it comes to stress in the form of torsion. And so it reached the fracture point, and the whole bridge collapsed into the river below. So resonance, like we say, is the result when a driving force is provided at a frequency that matches the system's natural frequency, there's some large increase in the amplitude. We can see that in this graph. Greatest amplitude comes when the driving frequency is the natural frequency. And that graph is the result of graphing this equation. And this equation is what you get when you have three forces. When you have a force governed by Hooke's law, a force governed by fluid resistance, and a force that comes from continuously driving the system, not too much unlike you continuously drive a system when you push a child on a swing set.